Hello, this is Kevin Meckler, and in this video I'll be going over my makeup lab for Lab 4, aliasing and sampling, and Lab 8, operational amplifiers. As you can see in the two pictures here, Dr. Mitchell has given me an exception for both labs, so the 30% deduction has been waived. I'll start with Lab 4. In this lab we study sampling rate and aliasing. So my code for this lab is shown right here. We have two inputs. Potentiometer determines the sampling frequency, and then we have a signal generator that's used to obtain the sampling rate. So we have four different sampling frequencies, 100, 142, 200, and 500. So I will now show the operation for this. This video I show how we generate a signal using the signal generator. So in this case we are doing a sampling rate of 500 hertz based on the position of the potentiometer, and then we have to switch frequencies. So we start with the 75 hertz frequency, 2.5 amplitude, volt to peak, and a 2.5 offset. So once we change the frequency from 75 to 100, we'll see the change in processing here on the right, and we also see the time domain and the frequency response. So we change that to 215, the value will also change, and then if we change it to 300, we see the same process. The four sampling frequencies that we have are 500 hertz, 200 hertz, 142 hertz, and 100 hertz. And for each one of those four frequencies, we test the signal with frequencies of 75, 100, 215, and 300 hertz. So we can see the results here in these screenshots. The sampling rate is shown here at the bottom. So this is for 500 sampling rate, 75 hertz, 100 hertz, 215 hertz, 300 hertz, and for sampling rate of 200, a signal of 75 hertz frequency. We see the sample rate right here, 201. 100 hertz signal, sample rate of 201, 215 hertz signal, and the 300 hertz signal. So the same is shown here for the sampling rate of 142 hertz. I'll scroll through the pictures. Feel free to pause the video if you want to confirm the details. And lastly, the sampling frequency of 100 hertz. So all of the images shown above were used to obtain the data shown in this table. So we see the sampling rate, 500, 200, 142, and 100. This is the actual value for the VSA data. That processing code was provided by the instructor. And for each one of the signal frequencies, we have the Nyquist rate, the alias frequency, both the theoretical and experimental. And as we can see, the results are very close to what the experimental results are very close to what we would expect to see theoretically. My calculations for the alias frequencies are shown right here. I'll scroll really quick through it for the sake of time, but feel free to pause it if you want to verify them. But here is the overall process. 500 hertz signal. So we obtain this value that then is multiplied by the sampling frequency over 2. And that gives us the alias frequency. For exercise 2, we also study the response of a square wave as well as a triangle wave. This video we see the square wave at a frequency of 10 hertz. So in this case, we do see here at the bottom that we have harmonics. So there is no aliasing in this particular wave. What that means is that the bottom section, the frequency, can be represented by a sum of different sine and cosine waves. In the previous images that I showed, there was aliasing, so we did not get to see this harmonic phenomenon. The second part of exercise 2 consists of generating a triangle wave with a 5 peak-to-peak amplitude, 5-volt peak-to-peak amplitude, 2.5 volts offset, and this signal has a frequency of 10 hertz. As we can see here at the bottom, the sampling rate is approximately 500 hertz, and we see that in this case we do have aliasing at about between 10 and 12 hertz. Here are some pictures with better definition. So this is the square wave for exercise 2, and we do see harmonics here. And for the triangle wave, we see that there is an aliasing frequency at about maybe 11 hertz. In closing, for this lab, the rubric has exercise 1 images, which have been shown at the beginning of the video, based on the readings obtained from the processing code that was given to us by Dr. Mitchell, which, by the way, that brings me to that. Here's the code that was used for the processing reading. So the information obtained there was used to complete the table for exercise 1. The calculations were shown. The square wave demo was also shown, as well as the triangle wave demo. So that completes the lab, and here's the rubric. Thank you very much. I will now be covering Lab 8, Operational Amplifiers. The rubric is shown here. We go over different amplifier circuits. For this specific lab, we do have a color scheme for all the wires, and this is going to be shown as well in the videos that show the operation of the circuits. My Arduino code has been included in the attachment for this assignment, but I will show it here for exercise 2. We have 3 inputs, and the readings are then obtained from the op-amp chip and are sent to the serial ports so that they can be read using the processing code, as you can see right here. So this code generates the oscilloscope-like application, and we will be showing that here in just a second. The first circuit that we cover using operational amplifiers is the comparator circuit. So we can see here the chip is connected to a potentiometer that basically switches output between 2 saturated states, and this LED will be in either one of those 2 states. So there is the dim state, as you can see it right now, and then as I switch the voltage, we will see the bright state. So it's just 2 states, and if we switch back and forth, it goes from dim to bright. The second circuit that we review is the non-inverting operational amplifier. So that is the circuit that we have right here. In order for us to find the output and the gain, we need to do KCL at the node right here. So we know the currents, and then as we do the KCL relationships here, we start solving for V out, and then the result is V out is equal to V in multiplied by R2 over R1 plus 1, and that is the gain for non-inverting operational amplifiers. The next circuit that we will cover is the unity gain amplifier, or the voltage follower, as shown here in the screen. In this case, the input is equal to the output, so the output will follow the signal that we receive from the input. So you can see the circuit is the one right here in the middle, and it's also controlled by a potentiometer. Here is the operation of the circuit. You can see that as we go down, the input follows. Right now, it's a little hard to see, but you can see the white signal right there showing the input, and the blue is the output. The one thing to notice is that if we go below approximately 1.7 volts, the output is unable to follow the input, and that is due to op-amp specifications, and the railing takes place at approximately 1.7 volts. But as we go back up and we pass that threshold, we see that the output follows the input again. The next circuit is the inverting amplifier. So the circuit here in the middle shows the op-amp and we are feeding 2.5 volts to the non-inverting terminal, and that is being accomplished by a voltage divider that can be seen right here by the cursor. We want to have a gain of 10, so we're also using a 1000 ohm resistor and a 10,000 ohm resistor so that we can get that gain of 10. So I will now show the processing readings for the inverting amplifier. So the inverting amplifier has an output signal that changes in different direction uh, to the input signal. So we'll be able to see that here. It's also important to note that the output signal plateaus at approximately a little over 4 volts for the upper end and slightly below 2 volts for the lower end. So you can see how the signal is inverted. The last circuit that we will go over is the integrating amplifier. So my analysis here, we see an integrating amplifier circuit has one resistor and capacitor. So if we do KCL at node 1, we know that the current going through the resistor is the same current going through the capacitor, as there's no current flowing into the inverting terminal here. So then we can do KCL rules and relationships. So VN over R is equal to, and we know that IC, current through the capacitor, by the terminal relationship, we know that that is the value of the capacitance multiplied by dVdt, dVc dt in this case, value across the capacitor. So once we have that, we integrate on both sides. We end up with 1 over RC, integral of input voltage is equal to the voltage across the capacitor, and we know based on this relationship and the negative feedback that the output V out is equal to negative VC. So once we do that, we add a negative sign, and we have that V out is equal to negative 1 over RC, integral from 0 to t, V in as a function of time, and we can then convert that form into this one. And if we simplify it, based on the impedance, we get that V out is also equal to negative 1 over the imaginary number here, omega RC, of the input voltage. So we will now analyze the circuit. Here is the one here on the right. We see that we have a 10 microfarad capacitor and a 4.7 kilo ohm resistor. And that is the circuit that we're using. It's also controlled by a potentiometer. We see the signal here. So an integrator circuit, what it does is that the output, we see here the blue line is the integral of the input. So we see the behavior of the capacitor there as well. But this is easiest shown if we create the equivalent of a sine wave. We see a square wave at the top, and we know that the integral of a sine wave is a square wave. So of course this isn't exactly a square wave, but the overall waveform is shown. So that is the integrating circuit. And in closing, here is the rubric for this class, this lab I mean. We have the competitor circuit. We displayed that circuit using an LED and the 2 saturated states. The analysis of the non-inverting operating amplifier was also done at the beginning of the video. And we showed the unity gain buffer and how the output follows the input, except when there's railing, and that is when the input goes below 1.7 volts. We showed the inverting operational amplifier, and we did that analysis, as well as the analysis of the integrating op-amp, as shown right here, and the demo of the integrating op-amp. So we generated a sine wave, and the output was a square wave, which is the integral of a sine wave. So that covers everything for this lab. Thank you very much.